I beg, reduce your volume. You help me a lot. If possible, drop you wearing your headset. Alright, let's get started. Book in the pussy. What kind of name is that? What kind of name is that, chat? What kind of name is that? Anyways, let's get going. The 6 step 1 algebra. For today, I mostly do maths, but then I have a little project I want to work on concerning computer vision, because I also did a course on filters, so I want to visualize how filters actually work. Step 1 linear algebra. We'll go with these other vectors, dot products, matrices, matrix multiplication, convolution as per the computer vision, derivatives and gradients, Sobel, Prewitt Laplacian, those are the kernels I was talking about. Then build the visualization in Python OpenCV. Alright. First question before I teach it, let's see. Calculate this, and this. Give me your best attempt even if you're unsure. Okay. What is a vector? Actually, I did this already once, but anyways. A vector is a component. A vector is a quantity that's both magnitudes and direction. A vector is a quantity that has both magnitude and direction. Okay, number 2. Calculate 2, 3, 4, 5. So that's how they did that product actually. Dot product. How did they do dot product again? Forgotten. Okay, I think I know. Dot product will be. I don't know dot product. I don't know that good. No, just try. Into 4 is 8, and then 3, 5, 6. I think that's for that block. Then number 3. So what do you think this matrix represent? 1, 2, 3, 4. It's a 2 by 2 matrix now. A 2 by 2 matrix. What else is that? Can you multiply this? It didn't say if you should multiply. It just ask, can you multiply this? So let me see. 1, 3, 2, 4, 5, 6. So can you multiply this? I think it's row by column. So row by column. I don't think you can multiply this. Is it column by row? Yeah, this column by row. So this. Yes, can we multiply it? Okay. So let me get my answers in. So the vector. The vector is a quantity That's both magnitude and direction. So number 2, calculate. So answer, I might fail this one. Answer is for 15. Oh, 8, I mean 815. 815. Third one. Third one is a 2 by 2 matrix. I don't know what else to see there. 4. Yes. These two matrices can be multiplied. Like I think that's about it. So we've got this. It's row by column. It's column by row, column by row. So this column multiply this one, this column multiply this one. Let's see. Okay, vector is correct. Dot product, small product. Okay, 2 by 8. Okay. So it's not just ending up a dot product. Okay, I have no idea. Dot product proceeds, produces a scalar. Oh, so dot product produces a scalar. Note that a dot produces a scalar. So I'll highlight that. Okay. The product produces a scalar, so we add the products. 2, 3, 4, 5, and that 8 plus 15. Okay. So 2, 3, dot 4, 5 is equals to 8 plus 50 equals to 23. Okay, this is very important in machine learning because you constantly encounter expressions w dot x. Okay, where a vector of weights interacts with a vector of input features to produce a single number. Okay, so matrix is understood but incomplete. Yes, it's 2 by 2 matrix, but I want you to think. So there's 2 rows, 2 colors for elements. That's actually, I will come back to this. And importantly, a matrix can represent a transformation. Okay. A matrix can represent a transformation. Okay. This represents transformation. We'll come back to this. So matrix multiplication. When it's tried that you can multiply, but let's actually do it. Yeah, but didn't such multiply, just so can this be multiplied? So the first matrix is 2, the other is 2 by 1. The inner dimensions match 2 by 1. Therefore multiplication is possible. Now we'll calculate row by column. First row, second row. Therefore that. Notice something interesting. Matrix multiplication used dot products. The first output is, second output is. This connection is extremely important. Okay, the connection we're building, you're going to see this pattern repeatedly. Vector, dot product, matrix multiplication, convolution, gradients, neural networks. below, watch past the fundamental script checkpoint. Let's see if that clicks. Yeah, that definitely clicked. Anyways. Did I even mention today? Today is 28. 2026. Okay. So this question 5, in my case, calculates 3, 4, 2, 5. That's the dot product. So 3 times 2 is 6 plus 4 times 5 is 20 plus 26. That's the first one. Question 6 in this case. So calculate 2, 0, 1, 3, 4, 4, 5. So calculate this will be equal to 2 in bracket 4 plus 1 in bracket 5, 0 in bracket 4 plus 3 in bracket 5. Okay. So that will be 8 plus 5 is 13, and then 0 plus 15. So for the second one. Question 3. Conceptual. Why is this multiplication impossible? 2 by 3, 3 by 2. Don't just say the dimensional match, tell me which dimensions need to match and why. Not help it, but anyways. Question 7. Okay, don't just tell me. So this dimension don't match, but 3 by 2 times 2 by 2 match, or at least the columns, the number of columns of the first row has to be the same, has to be equal to the number of columns of the second row, number of rows of second matrix. Okay, I've got my answers. So answer for number 1 is first question. In our case, between 6. Question 2 is is 13, comma 15. Question 3. So the dimensions do not match. Let's 3 by 2. 3 by 2. Simple puts the number of columns in the first matrix must be equal to the number of rows in the second matrix. Okay, let's see it. What you are correct. And number 3 is already the way I wanted to articulate the number of columns, so the first matrix must be equal to the number of the second matrix. Yep. 26, 30, 15, that is So can we go to the next? Okay. Now let's make it more interesting. What does the dot product actually mean? Okay, so far we've treated it as a calculation, but for AI and machine learning, I need to develop intuition. Imagine we have two periods. So it presents a person's future, so some future to another future. And W45 represent an importance that's we assigned to these features. Then x dot product of y of w will be this 23. So we're essentially saying take each feature multiplied by the corresponding importance, they add everything together. That's the basic idea behind a huge amount of machine learning. Okay. We'll learn more about that. Now connect this to our filter project. Here's what today's fun project starts becoming mathematically interesting. Suppose we have this tiny grayscale image. Okay, so it's a representation of an image is a matrix, and this kernel has a filter. So this is the Sobel. That's the Sobel filter. Okay. Yeah, so the Sobel X filter. Okay. What happens when we apply the kernel to the image? Oops. We essentially perform element-wise multiplication followed by a sum. Okay. Okay. Calculate that, your challenge. What is the resulting value? Don't worry about the entire image yet. We are going to use this tiny calculation to bridge dot product, matrix, kernel, convolution, Sobel, edge detection. That's something I need to do now, but why not? So, wait, let me just calculate that. I don't really need to write that down. The resulting value, let's put it here. So we came out of that. So this one's easy. This one is 0. This one is just dead. This one is 80. One is 0. Oops. This one is negative 8. Okay. This is negative. That is just 0. And this one is 50. Okay. Exactly, set up correctly. Now let's finish the calculation. Wait, I'm supposed to add, oh my bad, I'm supposed to add that. So we'll get a 20, a 40 and a 20. So the total is 20, 40, 20, what are we adding all three again? I don't know. 80. Okay, you just perform the convolution operation manually. More precisely, you took the image patch and the Sobel kernel and calculated this. Okay. So this is the same fundamental operation we will eventually implement in NumPy. Okay. But here's the important question. Why did the Sobel kernel give us 80? Look at the kernel. Okay. Notice the structure. Left side negative, it is 0. Right side is positive. So the kernel is asking, is the density on the right different from the density on the left? Okay. If there's a little difference, small response. If there's a big difference, large response. That's why it detects vertical edges. So think about this image. Okay. Oh, no changes. Okay. If we apply Sobel X, that is Sobel, basically this for vertical edges. Okay, what do you think will be the results? And then consider this. What do you expect the Sobel response to be for this? Don't calculate it if you don't want to. Just tell me what you expect and why. So for this image, let's if I can copy this. So for this image, it's not that it's calculate. No, that's good. So for the first image, let me see. No edge should be detected. Because the total output will give us 0. That is correct, as all elements in the matrix are identical. Bracket, in this case 10. So in the second image to consider, there is a clear difference. Okay, let's see now. Very strong response, and there's an important detail here. Okay, the Sobel kernel isn't directly equal for edges. In measuring a change in density, we interpret a large change as an edge. Okay. Now let's make the connection to calculus. Here's where today's mathematics becomes really useful. Remember what a derivative tells us. It measures how quickly something changes. For one-dimensional signal, the derivative, discrete derivative. That's essentially what Sobel x is trying to estimate. So now we have Sobel is approximately equals to a discrete derivative. That's a major conceptual connection. Why this matters is here. You're no longer seeing this as isolated topics. Calculus, derivative, rate of change, image intensity change, Sobel kernel, edge, computer vision, machine learning. That's what I want you making throughout this preparation. One more challenge before we move to the actual Python project. Why are you moving to a Python project? Consider this simple horizontal intensity profile. Okay. Imagine moving from left to right. Push up. Where would you expect the strongest edge? Between 10 and 50, that's where you expect the strongest. Question 2. Would the derivative slash change be approximately 0 before the transition, large at the transition, 0 after the transition? Explain why. That's going to be hard. We are going to use Sobel, Prewitt Laplacian, and after that we will actually build the visualization in Python slash OpenCV. Okay. So question 1. I expect strongest edge between 10 and 50. Between the text and the first 50. So will the derivative change be approximately 0 before the solution? 0 after the solution. Derivative, rate of change of something. Okay, let's try and figure this out. Zero before the transition. Yes. Large at the transition. Yes. Yes. Because the derivative is basically the rate. Zero for the solution. So will there be a rate of change? I'm really confused now. Will the derivative change be approximately 0? Because on the transition, you have a massive jump from 10 to 50, which we did not have between the first and second term. Between the first and second 50. I'll leave the explanation there. Let's see. Okay, we identify key idea. The derivative is small, 0, where the signal is constant, and large, where the signal changes rapidly. Yep. So we can take approximate changes as between here is 0, between here 0, between here 40, between here 0, between here 0. So the edge occurs between 10 to 50 transition. Okay. Now let's make one important decision. Okay, this is solid points that will matter when we get to Sobel versus Laplacian. First derivative. Sobel and Prewitt are essentially trying to measure the IGX and the IGY. So digital changes in intensity. Second derivative. The Laplacian goes one step further. So Laplacian, the second derivative of the intensity with respect to S plus the second derivative of the intensity with respect to Y. Okay. Know that. So it measures how the rate of change itself is changing. measures how the rate of change itself is important. That's why Laplacian behaves differently from Sobel and Prewitt. We'll visualize this rather than just memorizing it. Okay, visualize this rather than memorizing. Sobel was Prewitt Laplacian. Okay, think of our three filters this way. Filter mathematical main purpose. So Prewitt, first derivative approximate, detect intensity changes. Okay. Sobel, first derivative plus more wind. Okay, and it has also smoothing. Okay. Detect intensity changes slash edges. Laplacian, second derivative, detect rapid changes in intensity. Oh, okay. The interesting difference between Sobel and Prewitt is actually quite small in the basic kernels. Yep, this is Prewitt and this is Sobel. Notice the middle, Sobel gives it twice the weight. So Sobel basically say, I'll pay more attention to the pieces immediately along the center of this neighborhood. Now let's test your intuition. Consider these two one-dimensional signals, signal A, signal B. Oh, okay, signal B. Change here, not to rampant. And yeah, it's 10 to, and it's 10 to, and here it's 10 to. Interesting. But the change here from here, and then it's a 10, and then it's a 10, and then it's a 10. So but go from 10 to 50. Both go from 10 to 50, but okay, they are changing differently. Yeah, from here is 0, from here is 0, from here to here now it's 40 as a change, then here back to 0, back to 0. But from here the change is 0, from here say the change is 10, and then it just stays 10. So they still change, but now it's 10, 10, 10. Okay, we'll go from 10 to 50, but that changes differently. Question: which one do you expect to produce the stronger edge response, A or B? The stronger change response. Oh, what are the why? Okay. Which one will create to produce a stronger edge response? Now I'm really confused. How is it going to be? Which one is going to produce? I think signal A will produce a stronger edge response due to the really large change which occurs. So signal B has minimal changes, but they are smaller and eventually become identical, and eventually the change is constant. Okay, change from 0 to 10 to 10 to 10. Okay, I see the answers. Exactly, signal A is a stronger edge. Oh, I got it. Alright, this is good. There is one small refinement. Okay, thing is, so after the sharp flat region, the rate of change is relatively constant. That's what I said. That's very different from A, or what very hard, large rate of change. So a sharp localized change, strong edge response. A gradual constant change, weaker edge response at any single location. That's an important piece of intuition for computer vision. Time to build. So we will now establish a mathematical change. First change in intensity, then derivative, then kernel approximate derivative, convolution, and then Sobel Prewitt. And eventually image gradient feature computer vision. Okay. Build a tiny convolution engine. Okay. a Python project though. Alright guys, excuse me for a long moment. Yeah. So this chair is breaking itself. So when I was working on this, but basically it's an edge detection filter. This is the code here. I did this using Prewitt, but I want to show you two images. What are they? The actual image, actually the actual image, I see shapes. Yeah. Will you open them? Oh. Yep. So this is an actual image. I want to identify the edge. Yes, is it. Once I identify the edge here using computer vision, basically using filters. So we just did the filters, mathematics that does the edge detection using matrices. So now let me show you what I use with Prewitt. I'm not seeing any shapes with Prewitt. Okay. I guess we're going to run that. Let me double check. Prewitt output. Okay, I think this is it. So we come here. There you go. So this is how the image was. And now using the Prewitt filter, this is what we get. Can I zoom? Yep. So you can see here now anything that is dark, so the matrix comes at each pixel. Anything that is dark remains dark, but once it gets that large rate of change, it's going to now detect that. And now if inside the circle, like for example, so between here and here they say use change from black to white, right? So you use change, so you're going to detect that edge, and then inside here it's white to white, so no change. So you just set 0. That's what I'm saying here. Use change, it detects the edge, no change, sets it to black. Okay, so now I want to create another because it's just an edge filter for 3 kernels. The Sobel, Prewitt, and Laplacian. Now this is on test and this is the result. As so my image I was here a long time ago. Let me show you how it was. So this is how it was. Then this is the Prewitt. Let me show you the Laplacian with no threshold, crazy, and then with threshold and kernels. So this one is even more dense than the Prewitt because the Prewitt just looks for changes, but not like heavy changes, like just the slight, like the change with the highest value is going to identify it, but anything else like you cannot really get too deep into the changes. But unlike that, Laplacian looks for the edges in the x and y coordinates, and again any slight change in the matrix value or in the why is mine okay, there it is. So I zoom here from like the line test here and here are different, you can see. So it's going to detect that change. Maybe on my forehead from here to here is different, from here to here is different, so it's going to detect all of that. That's why you can see it is extremely bizarre, I would say that. Whereas the Prewitt is actually kind of clear, because you cannot really detect that change in light from here, from my forehead here, or even that change in this, that was from here to here. Okay. Oops. But now I want to create another one to actually get another Python script to actually get this really visible, not just the output. Okay. So those are the matrices, by the way. Let's come here. I already did this, so I'll just show it to it. So the is a way to display a filter over a live footage in OpenCV. Like I don't really know how this is going to work out, but it's just something I want to see how it's going to be. Since I already understand how the filters work, but now I want to see it in live, like using this very camera to see how it works. although the deep inner cells of it have kind of gotten a glimpse of it. So using the webcam, Sobel outputs, but actually use a Prewitt more than Sobel. Prewitt is more, how can I say, it's lighter. It's lighter. So okay. So the goal will be more than just webcam Sobel output. I'll make it interactive visualizer where you can see the kernel and the resulting filter live camera filtered image. Okay, active kernel. Okay, let's just use Sobel. ASPQ. So Sobel, Prewitt Laplacian, SY only. Wow. And eventually add this grayscale origin quick. So live Sobel, create live filters. NumPy. Okay, no, I'm going to put this here and then this here. So edge detection. Should I put the knife Sobel? Yeah, I'll just create one. Oops. Nice movie for me. There it is. Live filter. Trust me, I'm very bad at naming project directories, so I'll just put live filter. Live featuring, live. That's live filter. Let's just go live filter. Then inside live filter, I'm going to create a Python. I'm going to name it this. Okay. So I'll put this in it. Okay, just using Sobel. Okay. I'm going to off my camera and I have to show this. So okay. And when you run this, you should get two live windows. One is your camera, the other is Sobel response. But here's what I want you to notice. Not just run it and say cool. Move your hand in front of the camera. What will happen when you hold your hand completely still? Move it to the level where you should start seeing mathematics which just discuss happening in real life. The camera is producing an image, the intensity xy, the kernel is estimating the intensity at the x-axis and the resulting image is showing us where the change is large. Okay. One important thing about your existing codes. First of all, paste the code. Okay. So you use Convo 2D, whereas here we're using CV2 filter 2D. It's intentional. Don't throw away existing implementation. No, of course not. Your current project is valuable because you have already implemented a mathematical operation yourself. Now we're going to compare your convolution, NumPy and ski pi and the live camera against OpenCV filter to the live camera. Okay, I will take it much further. Original camera, filter camera, kernel, Sobel, Prewitt Laplacian, and V3 code. Okay, version 3 will actually show a small highlighted 2x3 in the picture of the live image alongside the live metric. Okay. So I'm going to have to wait. I've not downloaded it. Okay, this is not in. This was not downloaded. So install this. Yeah. So I'm going to install that, and I have to stop my camera because I want to. It's going to show this live. Like it's going to show using OpenCV. It's going to show the actual original camera and then the filtered one using Sobel. Is it even downloaded? I'm not seeing it. So let's show you. Okay, here it is. So it's downloading that. It's been downloaded. Alright. So time to off my camera first and my webcam. Let's off. turn off my webcam. Oh, what did I do? Alright, so bite my camera. Is that not how you're supposed to my camera? I believe you should not be able to see me now. So I'm going to remove this. Now you're not able to see me. That's okay, I'll be right back. So now it's just this. I want this to disappear first. Okay, let's run this. Now we should be seeing two windows open because my camera is back on now. Still waiting on those two windows to come on. It's gonna take a little while, just bear with me. It's taking a little long. Let me just be double checking on this. Yeah, over here is OpenCV.image show original and then image show Sobel X. Still taking. But the camera is on. I can see it from like the way my laptop itself. The camera is back on. And nothing showing yet. It's been an eternity. It's supposed to get okay. Oh, okay. Wow. It's so interesting to see this live. And it's like it's near how can I say near identical. Can I say identical? No, not identical. It's like real time. It's like real time. Let me see if I can break it. The calculation is instant. Okay, because always the second one, the Sobel X, right? Like I saying here is calculating in real time. The computer is doing the tricks what we're doing basically previously. It's doing it in real time and it's giving back the image. It's doing it image by image, so like frame by frame. It's interesting. Right now the light is not the best, and so there's so much change in intensity that I have to calculate. Like my face though. Face not as best as when I saw it from the image. Like the Sobel was giving it good when it was from the image. But this is not bad yet. But you cannot really identify. Can you really identify this as a face? I'm looking at it from the Sobel, but it's yeah, I can see my nose. If I point myself right at from the light source, because my light source is just up here. I can even point from the mirror. But if I go a little bit back, okay, I really can't see my mouth or my eyes or my beard even. Okay, let me see. Can't see my beard from the Sobel. It's really amazing. Let me see if that yeah. This is crazy, man. Can you see my hand? Yeah, you can see my hand. See? You can even see the lines. Damn. The intensity. Notice when the intensity is identical, it's just showing all black there. But once it's a change in intensity, you see the edge. Oh, even the edge itself of the hand. Can you see it? Not exactly, but yeah. You can see some edges at the middle of the hands. That's crazy good. Okay. I think this is just the first step, and traditionally this is how they were using computer vision, using filters. Right now we're using the Sobel filter. Also going to look at the Prewitt and the Laplacian, and then sooner or later we'll create a convolutional. Is it convolutional? Yeah, this convolutional neural network. But this is cool. I think you press Q to stop this. So yep, stop it. So we've done this. Convert to gray. Okay, now you converted to gray. Okay, we'll have any of those functions because eventually I would like to change this into different options, not just Q to exit. So okay. Okay, so the code responded as required. So perfect, that means the basic life pipeline is working. Camera, grayscale, kernel, convolution, edge, response, display. Now let's make it a real visualization tool rather than two separate OpenCV windows. Make the filter switchable. Yep, this should be cool. So I'm not gonna replace. I just create a new one because now this live filters. I believe it's going to give different kernels. Yeah. Therefore, I'll first rename this refactor, rename live Sobel live Sobel kernel. So it's like kernel, not kernel. Okay, refactor that. Now I'm going to create another Python file called live filters. I'm going to copy and paste this. Then we're going to look at this. Let's try to look at it for me. So OpenCV and then NumPy for our kernels. This is Sobel. This is Sobel in the X axis. This is Prewitt in the X axis. And this is Laplacian. It works both X and Y axis. So then it's going to on our camera. If not camera open, it's just to test if the camera is open. If it exists. Current filter Sobel. Main loop. Okay, in the main loop again it checks whether it gets an output from the frame, and then mirror the camera so that it should be like the left is left from the camera and the right is right from the camera. Convert to grayscale, okay, and then get current kernel. Okay, apply convolution. Okay, convolution is basically mean multiply the matrix of the image by the matrix of the kernel. When you do that mashing, it becomes a convolution. So gray, CV2 this and kernel. Okay. I still wonder what is this for. Wonder CV2 CV underscore to F. I don't know what that is. We'll check that later on. So absolute value filtered. This is absolute value filter. Convert to displayable image. So after doing that, because we work on OpenCV is going to convert the image from OpenCV into a matrix. After I've done the convolution operation, we're going to convert it back to an image. So that's what's happening here. Then display filter name. So if you put text, just put the filter name, current filter, okay. Put that, okay. Show windows, it show on the frame, and then the filter. That's live camera, and then the filter. Keyboard shortcuts. So if S is pressed, go to Sobel. Okay. Else if P is pressed, will be Prewitt. L is pressed, will be Laplacian. Then clean up and then do. Okay. Try this. Then run Sobel. Then Prewitt the Laplacian. Watch how the live edge representation changes. And don't worry about coding for the moment. Put your hand in front of the camera and compare Sobel and Prewitt. As I said, why does this filter look so similar? Well, Sobel and Prewitt look similar because of the matrix itself. If you look at the matrix, let me show you for me. If you look at the matrix, they are almost the same. The only difference is that Sobel has more smoothing. You see -1, -1, -1, -1, -1. So it's more of the same. Just that Prewitt is a more simplified Sobel. Sobel here, it's both of them are first derivative, and Prewitt is more simplified because you see here, it does not really carry more weight in the center. That's like basically the best way to explain it. Sobel carries more weight in the center, and it's also good at detecting noise, especially from the center point of view. Okay, then compare one against Laplacian. Laplacian basically has just made differences. First of all, it is second derivative. This is first derivative. And secondly, okay, yeah, that's what I said. And secondly, it works in both X and Y axis. This guy works only in X axis. It can also work in Y, but that's only if you transpose them. If you rotate them like this. why does Laplacian behave differently even though so very identical? One more experiment. Keep the command printed in a fairly plain wall. Move your hand slowly across. Yeah, I don't have a fairly plain wall, but I'll see. And that's what I'm trying to do here. We're trying to test trying to have a fair background so that it's just going to show all black or I think all white. Then move quickly, watch the edge, rate of change. While you're experimenting with all things, the difference you observe. There will be a really cool part. Putting a kernel itself inside live publishing window and visualize the convolution process. Oh, this is cool. So when you run this will take a while. Oh, actually, no, I don't take so much of a while. Okay. So Sobel response. Okay, this is Sobel. So let's look at Prewitt. This is Prewitt. Wait, is this difference? Sobel is clearer. Sobel is clearer. So this is Mahani. Yeah, you can see the edges. Then this is Prewitt. Prewitt is basically the same except I don't even notice a bit of noise. You see here it's clearer. I don't really think I can say clearer. Like, you see here it's dark. Then Sobel is bright. See it's dark. You can see the edges from my face. You can also see here they're just clearer. I really don't know how to explain the why. But I think I did explain it that basically Sobel will be easily identifies noise. So that's why thanks to the smoothing that is basically the weight that it has at the middle, which is better. Unlike Prewitt. Now let's check Laplacian. Laplacian is so I didn't expect it to be so dark. Is it because of the lights? It's expected it to be a lot of light, it's a lot of white everywhere. The edges that it gets from me. I believe it's because of we did some kind of normalization. And let me show you. I remember seeing it. Yeah, over here, absolute value. Convert this absolute value stuff. Like if you remove it, then you won't have it this dark because Laplacian is supposed to be better, you know. It's supposed to be better. Oh, I see this. I don't think Prewitt can see this. You see here the difference here. Oh, you can see from the original camera. So here, like if okay, I've raised this right. Prewitt has still not seen it. Even Sobel, but Laplacian, given the intensity because instead of the light is low. If I come close to the camera, you can see this. That's interesting. You can't really see my hand there. Okay, you can see the edges. You can't really see the edges. I like Prewitt. Prewitt is clearer. That's nuts. I thought Laplacian would be clearer. Even Sobel is even more. Is even clearer than. Look at Laplacian. Are you for real? We gotta investigate on this. Laplacian is supposed to be like the clearest effect. Supposed to like detect the faces. Oh. Okay, now never mind. What's that? Is it detecting now better? No. Well, it's not clearer, but it's detected. Like, see my hands. It's able to detect it on my face too, my lips. Let me see with Sobel. Sobel is clearer. Is it that a noise or is it going to look alike? No. And it's getting the edges well. Like I can see the edges of my neck and the shape of my head. And Laplacian. What edges are you seeing? It's not seeing any edges. It's not seeing any edges. Can you see the edge from my watch? Okay, yeah, it could at least get that. Can you get the edge from my watch? It's not bad. Or like Sobel, dude. No, Sobel is just clear. Yeah, look at even my hand. Look at my hand. Okay, not really that good. It's not really getting the edge from my hand, but let me see my finger. Yeah, you got the edge one. If you go to Laplacian though, the edge is not there. The edge is not there. Although when I go far enough and I'll see the edge. That's something to ask. You see here? You can see the edge here. Let me go back to Prewitt. Prewitt don't need to go that far. Okay, it's all dark now. That's interesting. Oh, the light, the intensity is indeed something. You see, my thumb is all closed up. and now the intensity all through my finger is the same, so that's why. Let me go back to Laplacian. Not much difference. Okay. We are good with that. Trying to stop. Okay, that one stops. So let me ask something to the eye. Why is Laplacian looks dimmer? Laplacian looks dimmer and shows less of the changes from the frames than Sobel and Prewitt. However, using images and my own edge filter program, I got better results. Better results from Laplacian. Like it identified all sorts of changes. Yes, that was actually very useful. Actually, I got that important. Why the old program looked better? The old program Laplacian boundary symmetry. Then result was normalized. Okay, normalization stretches the Laplacian response so the full 0 to 285. Our live version currently does this. That's very different treatment. Okay, suppose Laplacian produces values like 0 to 58, 12, 20. Those values are all relatively small compared with 255. Okay, after clipping they remain dim. Okay, but your old program effectively says the strongest response in the image is 20. Let's stretch 20 to 255, so you get 0, 25, 64. Okay, much more visible. It's another importance. The current live program uses only one kernel for Sobel X. Okay, so your original program goes this and this is true, then combines them. That is okay, that's the true. That's why in my old program Sobel was actually clearer, because it actually add Sobel of the x-axis and Sobel of the y-axis, and Laplacian just got it just used Laplacian. It's not really anything. Okay, so the old Sobel result is the daily changes in both directions. Our current live Sobel is only looking at those in the x. That's another thing we should fix. Okay, this gives us a better product. Instead of simply switching filters, let's make the visualizer mathematical nice. We'll have Sobel, and then add it, we'll have Prewitt, and then Laplacian. Laplacian really does this. Then we'll normalize every result independently for display. That should make the comparison much fairer. Okay, let's modify the live visualizer. Change the filter section to this. Is this how you had it? Did we use if? When did we use if? So this. When did we use if? Let's see if. Okay, let me just search. No, when did we use if? Let's use if. Just name to this. That's. They don't miss what you just discovered. Particular attributes. Okay. Why is there an if? That's right. Change the filter section to this. Is there a filter section? Let me see. Okay, this is the filter section. Now this is just a kernel. The kernels are the whole thing. Okay, so if current Sobel is equal to this, Sobel x is this, else if is this, Is the Sobel even in the loop? Current filter. Sobel. Okay. Make sure we'll unmagnified 2x3 pixel patch from the live camera and display the actual multiplication as shown. Okay. So let's just do all of that. Just add all of that in the code script. This version includes live webcam, original filter view, Sobel X, Sobel Y, Sobel magnitude, XY magnitude, Laplacian, automatic normalization, active kernel display, live GX, GY, and magnitude information. Oh, okay. A 2x3 pixel patch, the corresponding. Yeah, this is gonna be something if that actually goes through. Save this as convolution lab.py. Okay. I'll do that. Stop this. Let me save this. No, save it here. Convolution lab. 5 filter now. Keep it in here. Okay. Convolution lab.com. Yep. So it's gonna be pasted here. I'll just look what it does. Why does it have this? Why does it have this? Those are the kernels. So there's the kernel the X and then the Y transposed. Yep. Prewitt on the left on the X and then went to down. Prewitt on the right transposed and then Laplacian. Then the settings you have width and height. Then patch size 3. Okay, let's go 3x3. So position of pixel used for convolution demonstration. The point follows the center of the screen. Do we no padding? No padding is set. Something. Camera is getting set. Then help functions. Helper function has to normalize an image to result into 55 for visualization. Okay. Match value needed. Okay. Calculate convolution patch kernels. Perform the convolution calculation manually. Patch and kernel must both be two. Multiplication equals to patch and scanner. Total is return this. Draw kernel. So it is the panel, the kernel, XY and SL size. So without padding, it still gives us the 3x3 back. That's strange. Anyways, for column arranged way, x1, x2, this. Okay. Now at this point, you see this one shot. I really know the game. So honest. Draw a patch. So let's do this. Text size. What's text size for? Okay, no. All of these. Wait, mirror, camera, actual frame dimension. So grayscale, going to grayscale it. Then filter processing. Here filter is Sobel, going to do that. So else if filter is Prewitt, going to do that. Else is Laplacian. Okay, then a 3x3 patch. Draw location of patch. I really wonder how it's going to do it. Filter name. Draw title. Okay. 3x3 image patch. Okay, convolution results. I can't wait to test this out. Controls. Oh, I can't. I know. I thought I was able to control pixel by pixel and see the mathematics behind it from my camera and panel. Oh, the panel is where the pixels are. I believe so. Final output live and then filter response. Convolution laboratory. Keyboard S P L and then cleanup. We're going to run this. special laboratory rather than just a filter domain. Particularly useful part is that the center of the kernel has a green marker. The program extracts accurately between pixels underneath the marker, puts them inside an active kernel, multiplies them, and shows the results. The result is sum. Okay. Okay, let's try this. Let's run this. Now this is something. It's showing it all as one. That's crazy. Oh, I can't. I wish I could like make this bigger. Okay. Oh, but you can see this. That's something. Damn, now this is something. This is terrific, man. Wow. Convolution laboratory. I wish I had something with no colors. Let me see. Okay. I should get all 0. Wow, is this Sobel? Yeah. Wow. Then let me see. Let me put Laplacian. Laplacian, really? No different Laplacian. Okay. Oh, Laplacian is really dark here. No real difference. Let me put Prewitt. Prewitt is clearer. Wow. This is cool though. But I'd like to like get this expandable. Let me see. It's really set the width. I wish it could. It didn't. Resize camera and filtered image to fit side by sides. Okay. It's so small. Let me see. Maybe from here to make this bigger. Frame height and this. Like this. The brief is okay, but the frame height not okay. I think I should increase the height instead of the width. So let's go to where the height is. The height, panel width, height. Go to the height. That's at the top of this so low. Okay. Patch heights. Width, heights. Let me see. I'll change this to 1280. Yep. Then let's run this. Does this change it? Nope, not change at all. Yeah, never mind. Now to increase the height of the OpenCV display window. Right. So while that is searching, yeah, on the free plan. Okay, so very soon this project of mine will be done, and yeah, ChatGPT has just told me that it's all over for me. Currently the display is being determined by this section. Okay, so I'll go to our section. Am I there yet? Another section. Alright. Where is that section? Hello. Yeah, this is it. Okay, so the height automatically calculated from the width to preserve the camera aspect ratio. Easy solution. You simply want OpenCV window larger, increase these to 600. Increase both the height and the width. Okay. It says 600, I'll put 700. I really want to see how big it is. So this shouldn't take too long. Okay. Is it kind of slow? Yeah, it's slow. It's visibly slow. But now I don't know whether it's just the camera. No. But what I wanted to see was this calculations here. This is crazy. So you can see the active kernel here. The 3x3 image patch convolution results. The convolution results give the dot product, the total dot product. Okay, and then patch kernel. Oh, okay. From here, these are the results. There's a convolution results. Wait, this convolution results and the total right here. So it does this and this and this adds up. So that's how we get this. That's 60. Again, let me put this. Let's put this in and see what is it showing now. Great. That is showing approximately 0. It's not going like very large because you can see this dot here is showing the calculation from this guy, from this particular pixel. Like I can say, if I put here, the change should be massive. If I remove this, so there's still some change calculation, but that's because the intensity, the brightness. So if I have a truly white image, I should be seeing 0 or 3. That's not bad. So when Sobel, let's go to Prewitt. Prewitt, it's 0 the majority of the time because Prewitt is simplified. Let's go to Laplacian. Laplacian, wow. It's so dark here. It's also 0 majority of the time, but it certainly is dark. When you look at it from here, it's not really supposed to be the case. I don't know why it does this. Wow, Sobel is actually clearer now, especially as doing the edge detection in the X and Y now as compared to what we had first. Now this is cool. This is cool. I'm trying to see the Sobel. This is great. Open Laplacian. Laplacian is so dark. I don't really like it. That's not cool. It's not doing justice to Laplacian because Laplacian does the X and Y on the code, whereas in the Sobel, in this code, he has to do the convolution for the X axis, the convolution for the Y axis, and then sum it, which gives it I don't know, fairer advantage and things like that. Made Laplacian, it's just in one calculation, so it's supposed should be clearer. Last time it's 10:51, almost 11. Laplacian. Okay. Look at Prewitt. Prewitt is clearer. Okay, now you can even see this over here. Look at this Sobel. Yeah, so we can get it to the change. Wow. So as it stands now, okay, that's another detail. Notice how here it's actually the density here is higher than here, but it's just showing all dark here. That's the Sobel. Let me look at Laplacian. Laplacian is really dark. It's not giving it justice because this is not how Laplacian usually shows it. It's not giving it justice. Not just okay. What else could we make this code do? Framework. So what else could we do now? I use for visualization project. Drag the window edge to make it taller and wider. Okay. Because we add more mathematical information into the panel, you want control over the overall space. For visualization project, I'll use window normal plus the size window. Okay, so what's next now? Because all this is knowledge that I already know, which I followed from the course. Next, I'll take this from working demo to visualization learning project. So day 6. Next stage, separate the gradients. Right now, okay, when you select Sobel, you are mostly seeing this and this show. So let's make the application show the 3 things simultaneously. So command GNX, GNY, magnitude. Oh, okay, magnitude. Oh, this takes me back to my magnitude. Okay. So we have this, and then for Laplacian, what will we do? I wonder. Separate vertical and horizontal. Then comes a really interesting part. Compare Sobel period mathematically. Okay. And then understand Laplacian properly. This is particularly relevant because of what units earlier. And visualize its raw response before normalization and after normalization. This is what this is really what this is this. Is it the same thing? No. Why is there one everywhere? What? It's a different Laplacian. This is not what I know. And see how the 4 neighbor of 8 neighbors Laplacian behave. Okay. The aha feature. Okay. We see something like this. Cool. You move the mouse to another part of the image and the mouse change in real time. Click second and multiplication. It will connect it to a machine learning. Why don't we do that here? Once we finish the visual, we'll step back and ask, why should an AI engineer care about this? So, and you will see image convolution, feature map, convolutional neural network. Okay. Your little thing about this Sobel experiment is actually teaching you the fundamental operation of convolutional neural networks. We can build a tiny convolutional operation ourselves using NumPy. Yeah, that'll be another video because I still have to follow the course on CNN, so I don't want to cheat myself. So let's build version 2. So let's move. So let's close this version 2. Okay, copy this. Version 2. Is version 1 still? No, version 1 no. Version 2 is done. So let me see what version 2 does. Basically the same thing, right? Convolution Laplacian 2. Convert arbitrary floating point filter response into a visible 0 to 2 fit of image. So, draw image. This is cool. This is really cool. Now this code is just to visualize what we've learned. I'm set any new keys, not yet. Change codes here. Okay. There's one time I'm gonna have to change here it's the width. The height. I need to change that height. Resize, okay. Resizable window. Oh, that's cool. We have a resizable window, then that's cool. I need to change anything there. This code is long. Damn. Run it, then do this. Pay particular attention to this. Okay, one correction from my legislation. I was going to be precise about something. The Sobel X filter responds strongly to vertical edges because it measures intensity change in X. One version 2. And let's see now. Ooh, this is big. Okay. Wow. I believe this is Sobel. And then it's showing the magnitude was this is Laplacian? Why is it showing Laplacian now? That's what. Let's start with Prewitt. Maybe it's showing Prewitt. How do I even know it's showing Prewitt now? Okay, this is here Prewitt. But showing Laplacian either ways. Laplacian is clearer. That's cool. Sobel. Let me see Laplacian. Damn, Laplacian X and Y. Okay, left side are off because Laplacian actually. Yeah, let me see. Oh, but why is it showing Laplacian? Because it's good to show Laplacian over here. Laplacian so this is Prewitt, yeah. Okay. So I'll try something. If I put this way. Oh, this is cool. So the x-axis is capable of seeing the edges in the x direction. I say like the x-axis, right, is capable of seeing the edges that are running 90 degrees with y. The y is capable of seeing this edge here. The x can't see because it's moving around the y-axis. And then when you do the magnitude, you're able to see the entire visualize this. And don't forget the edge. That's cool. That's cool to actually do. Same thing for Sobel. I've turned to Sobel now. So you can see here from X, GX is capable of seeing this edge, but it's not able to see this edge. Then if you check on Y, it's faint, but you can see this edge. You can't see this edge. Then we do the magnitude, you can see the entire edge. Laplacian, okay, Laplacian can also see. You can see the edge over here and over here. Cool. And they have this sum. Second derivative, Laplacian measures changes in the gradient. Okay. Then let's see. Oh, okay. This is cool. Gradient information, convolution results. When the people that came up with this were just genius. Were just good. Okay. So mouse controllability, but we now I'll skip that. Rather than just a filter view. No, but this is cool as this. This is so cool. That's time. It's already 3. It's already 11 p.m. So I could learn how to filters. Let's see. So a Prewitt, Sobel, and Laplacian, the dominant. Well, I'll say where, because filters were first used traditional computer vision. So filters for traditional computer vision. Okay. Yes, they were among the most important and widely taught filters in traditional computer vision. But I wouldn't say they were the 3 dominant filters. Okay, so Sobel, main purpose filter, first order gradient edges, Prewitt, first order gradient edges, second order edges, rapid intensity changes. Okay. I cannot explain now why it was dark also. Robert Cross, simple gradient edges, Laplacian of Gaussian, smoothed second derivative edges. Okay. Carnegie, Gaussian blur, noise reduction smoothing. Wow, I like to try Gaussian blur. Okay. The important institution is that Sobel are individual convolution kernels. There are something like Carnegie is an entire edge detection algorithm involving several stages. And historically, there was a progression. The simplified picture is raw image, smoothing as Gaussian filter, gradient derivative that's using Roberts, then Prewitt, then Sobel, more sophisticated edge detection, Moses Laplacian of Gauss, Carnegie. The key problem with simple derivative filters is noise. Okay, differentiation amplifies high frequency changes and noise is full of high frequency changes. So that's why techniques such as Gaussian smoothing plus derivative becomes so important. Why Sobel became particularly popular? Sobel is really doing 2 things: estimating the derivative, applying some smoothing perpendicular to the derivative. That's cool. The two in the middle does like that. But here's a really important semi-level connection. Image cross kernel. Fundamentally the same type of convolution that appears in convolution neural networks. Okay. The difference is that in classical computer vision we designed the kernels this, whereas in CNN the network learns the kernel values from data. Let's see. Okay. And here, as per CNN approach, there's learning approach also. And I'll keep learning on the maths for now, which of the filters should I do it? Let's avoid the calculation part. Why not? Should I leave the calculation part here? Open version 1. I'll open version 1 and just let you know. In case takes place. Oh, version 1 is too slow. Let me see. Convolution lab, live filters. Let me see, how does this one respond? I believe this one is faster. These are secrets. Nope, not that secret. That's cool. So I'm going to leave this here and here, and then I'm going to just keep with my maths. Yes, cool. Oh, now you can see me. That's cool. That's cool. Okay. So, what are we supposed to work on in maths? What is probability? Let me just look at it for now. Skills. Can you leave the skills matrix? Is this skills matrix here? So I need to learn data structures and also deep learning, machine learning. So let me see. Statistics, math, statistics, programming algorithm. So algorithm, machine learning, and statistics. Which one should I go with now? We did do variance and the rest. But now I'm more supporting variance and the rest. We did it matrices. So what should we be doing now? I don't want to be choosing it. Now it's really tight. Let me check. I just want to check. What is 2bx expected as per service 12 covered for the math test to apply for CMU, for CMU masters. Okay, so we Carnegie Mellon University masters expected to establish linear algebra, matrix operation and potential, linear transformation and projections, matrix derivative. Okay, calculus, probability. Okay, Bayes rule. So I believe we'll try to work on this now. Yeah. Let's work on this now. Why did W1 now? Why did it W1? Level of them 1. Okay. Therefore, still with them 1. No matter. Okay, let's run these guys. Sure. Absolutely, this is the right point. This is the right point to switch gears from the edge filter project into mathematical formulation. For CMS, so just you don't try to cover all 3 areas at once. We'll walk through them in sequence where each topic supports the next. Okay. Our sequence. vector is represent three features. The vector itself doesn't have to represent a physical direction. That's an important distinction function in vector operation. Suppose for this and this, addition and this. Okay. Vector multiplication, understand that. Dot product. What is extreme vector? Notice something familiar? That's basically what we're doing with our image kernels. Okay. Sorry. Goodbye flopper. The convolution filter response is fundamentally a collection of multiplication and addition. Okay. That's one reason your filter project fits beautifully into today's mathematics. Sorry. That's one reason your filter project fits beautifully into today's mathematics. I wonder if there's a filter to convert my face into something else. That should be something. I wonder if there's a filter to do that. I'm really getting astray on this one. Let me just check. Is there a filter? No, I don't think it's a filter. I think it'll be an algorithm, not a filter. I believe so. Sobel face overlays. Our face filters actually work. Face detection, facial, llama detection, tools to get started, OpenCV, media pack, zip or fast Okay, so it does not. It's okay, it's cool. Face swap. And eventually I'll get back to this another time. So, images is essentially a rectangular arrangement. I'd like to spend 30 minutes, the next 30 minutes. What is this? I'm trying to read a message from my watch. Is it even under this? Oops. This is a message I'm not listening. Yes. I want to spend the next 30 minutes before I go to study. Where's my watch? Okay, it's not behaving. My watch not behaving. I'm trying to send my stupid watch. Good, 30 minutes. Let's work. Image is essentially a rectangular arrangement of numbers. Okay. Oops. Interesting. So, this is essentially a rectangular arrangement. That's 2 by 2. So A is an element of row 2 by 2. Rigid correctly identify this concept earlier. So matrix multiplication is where things become much more interesting. Okay. For For this to happen, number of columns of the first matrix is for the number of rows of the second matrix. Okay. Why this matters for AI? Consider a neural network layer. Y is equal to W, which is a scalar, X, which is a matrix, plus B, which is a matrix. The innocent looking equation is basically matrix multiplication plus vector addition. Okay. So the neural network performs this operation over and over. Yeah. So does this and then this. So when you are comfortable with matrix multiplication, you are already understanding one of the fundamental equations inside neural networks. Again, it's crazy that this video down is actually mathematics at work. It's crazy, man. It's crazy. It's not just programming, it's actually maths that can be proven. It's crazy. Your first year new start exercise. I use Python for this. Give me this and this, calculate. Yeah, that's starting easy, guys. So matrices. So A is matrix 2, 3, 1, 4, and B is matrix 5, 1, 2, 3. So question 1. Question is calculate A plus B. So A plus B will be 5 plus 7, 3, that's 4, 1, that's 3, and then 4 plus 3, that's 7. So that's question 1. Question 2 is A times B, vector multiplication. Is it vector multiplication? Yes, vector multiplication. So we have 2 in brackets. Is row times column, row times column. Is it row by column? So 2 in bracket 5 plus 1 in bracket. It is row by column. Okay. 1 in bracket 1, and then 3 in bracket 5 plus 4 in brackets 1. Okay, and then the second one is 2 in bracket 2. Okay, plus 1 in bracket 3, and then same thing, 3 in bracket 2 plus 4 in bracket 3, which is equals to, that will be 10 plus 1, that will be 11. And then down 3, 5, 15, 15 plus 4 is 19, 15 plus 4 is 19, 3 times 2 is 4, 4 plus 3 is 7, 4 times 3 is 12, 12 plus 6 is 18. So we have the addition, question 2, question 3, that's question 3. I don't assume A B is equal to B. Yep, A B is not equal to B. Yeah, A B is not equal to B. So question 2 is instead it's not equal to B. Okay, so it will be 5. Are you sure? Sometimes that may be the same. So it's 5 into 2 plus what? Plus 3 into 1. So it's like the same thing. 1 is to, oh, this is where the changes go. 5 into 2 and then 2 into 3. Yeah, it's not the same. And then you'll be 1 into 2 and then 3 into 3 here will be 5 into 1 plus 2 into 4, and here it will be 1 into 3. Yeah, 1 into 1 plus 3 into 4. So if this is not the same, I don't know. Let's see. That will be 10. 10 plus 6 is 16. That's not the same. That will be 9. 9 plus that, so yeah. 9 plus 2 is 11. Okay. Just double checking. Ooh. Yep. The next one. 5. 2 plus 5 is 8. 8 plus 5 is... Okay, yes, sounds outside. 8 plus 5 is 12, 13, 13, yes, 13. 13, yes, 13. Then 7, 3 times 5 is 7. Oh, I did a mistake somewhere. 3 times 5 is 12. No, it is okay. So this time is okay. 3 times 5 is 12. 12 plus 1 is 12 plus 1 is 13. This time I made an error somewhere, but at the same time I didn't. I have strong feeling that I did not. So let me try and give answers. Okay. Can't easily do this. Let's stop that. Answers. Question is question is 5, 2, and then 50. Oh, anyways, question 1 is 7, 7 and what? 7 and 2 above, and then below is 4 and 7. 4 and 7. Okay. And then question 2. It's question 2, and so let's do the skeleton. Question 2 is 11 and 7, and then 19, 18. Question 3. Question 3. Question 3 is building skeleton here. Question 3 is 16. Question 3 is 16 and 13. And then 11 and 13. So that's my answers. Let's see now. I said all three are correct, but shouldn't have been too hard. So I can't see my mouse. Where's my mouse gone to? Can't see my mouse and then no answers. No, okay, so it's okay. Okay. So we got this first time. We spent 10 minutes. So correct. Quantities. We have this 11, 7, 19, 18. It's not the same. Yeah. So A business and B industry. Okay, next linear transformation. Now we're going to make matrices visual. Think of a vector as an arrow, x and y. The matrix can take the vector and transform it. Oh, okay. So that's transformation. That's scaling. Scaling, yeah. That's scaling. Multiplying a scalar to a vector. For example, A is but these are two vectors. 2, 0, 0, 1 multiplied by x So you get this 2 2. Okay, so transformation changed 1 2 2 2 2. Okay, the x coordinates was stretched by 2 while y remained unchanged. Let's see. Okay, y remained the same once it was changed. That's good to see. This is the key idea. A matrix isn't just a table of numbers. It can represent an operation that transforms vectors. Matrix represent an operation that transforms vectors. Okay. This becomes very important in machine learning, especially scaling, rotation, projection, dimensionality reduction, coordinate transformations, PCA, neural network layers. The exercise: consider A and X. Calculate AX. Then tell me geometrically what happened to X. Okay, and just give numbers, tell me what X. Okay. So I'm going to calculate that. So we got A. A is 2 0 0 3, and then X is equals to 2 1. So we calculate AX. AX is 2 into 2 plus 0 into 1, and then 0 into 2 plus 3 into 1, which gives us 4 and 3. So answer is 1 3, and then you're going to explain why. Answer is I'm trying to delete everything. Okay, answer is 4 4,3. And geometrically what happened to X? So matrix X and Y. Matrix, tell me what the matrix did to X and Y. Okay, geometrically A really shifted because X was 2, Y was 1. So A transforms X from 1, 1 is 2, 1. I'm trying to split 2, 1 to 4, 3. Basically affecting the position of matrix X in matrix X in both X and Y axis. Okay, let's define it that way. Okay, numerical answer is correct. The geometric interpretation is also basically right, but let's make it more precise. That's just not precise. The matrix stretched. Okay, that's the word stretched. So the matrix stretched the vector by different amounts along the two axes. So I'm going to write that. So matrix A stretched the vector by different amounts along the two axes. Okay, so the matrix stretched the vector by different amounts along two axes. So X was stretched from 2 to 4, so double, while Y was stretched from 1 to 2, so it's triplets. Okay, I like to keep that noted. Should I? Yeah, I think I keep all of that. X, which was 2, was moved to 4. So it was doubled. Alright, and I could have seen this if I was not really in a hurry to answer. So 1 was 10 to 3, so it's basically triple. Okay. So the transformation systematically changes every vector according to the matrix. On the right-hand side, the matrix this represents a scaling transformation. Oh yeah, that's true. This was a scaling transformation. I'd like to get this highlighted somehow. Gosh, I'm also not sure to my notes. So this was a scaling transformation. It had this happening. That's the identity matrix. Nothing changes. If we had this, okay, that's an identity matrix, no changes. If we had something like this, we'll get a rotation. That's where linear algebra becomes much more interesting for AI. Different matrix encode different transformation. Next projections. Okay. So 2 is 0, 3. Scaling. Which is I'd like to get all these guys in. So 1 is 0, is identity matrix, identity matrix, and then 0, 1, negative 1, 0. This area is rotation. Let's convert something like rotation matrix. And there are several rotations from number 1. This is bigger. I mean, like, we can more view. Yeah, yes. So, for projections, how long? It's only 30 minutes, almost 10 minutes. Projection is especially important because it appears in things like least squares, PCA, computation, and dimensionality reduction. Okay. Imagine a vector 3, 4. Projection part of this. Okay, this was something else. Projection. Oops, no. Okay, why? Projection. So I don't with this. That's cool. Can't wait. So imagine a vector x equals 3, 4. So we're interested only in its component along the x-axis. Its projection onto the x-axis is 3, 0. We have essentially taken words. So imagine this vector, and then we're interested only in the component along the x-axis. Oh, okay. Its projection onto the x-axis is this. So we're essentially taking the 2D vector and extracted the path that lies along the particular direction. The general projection of x onto a vector u is projection of x onto vector u is equal to the dot product of x and u, the dot product of u and u times u of that times u. Oh, that's amazing. This formula is worth understanding, not memorizing blindly. So your first position exercise, given this and this, calculate this. And tell me what the projection means geometrically. What you get it will move towards region vectors, region values. Changes. And I did this in bachelor's degree. Region vectors. More or less. So first projection. They told me not to cram the formula, then they asked me for the formula. Or they asked me for what are you guys? Anyways, next question 4. Kind of feeling tired now. Can't really relax. Kind of feeling tired now. So, equation 5. We've got x equals to 3 and 4. Then we've got u equals to 1 and 0. Calculate x. So, number 1, calculate x dot u. X dot u is so that put it. So 3 times 1 is 3, so that will be 3. The second point is u times u dot u, that's the product. U dot u will be 1. U dot u is equals to 1. And then the third one is projection of matrix x to u will be equals to x dot u, the product of x dot u divided by the product of u and u, and then all that times u. So we did the product of x and u gives us 3, the product of u dot u gives us 1, and we multiply that by the matrix u. So that gives us 3. Whoa! Okay, that's cool. Jeez. That gives us 3. So it basically removed this basically removes the vector, the y component of the vector x. Yeah, the y component of the vector x. So tell me what the projection means geometrically. How do you want me to explain that? I'll try and explain this best I can. Let's try and be more precise this time. So x with u equals 3. Next one is u. I don't know how to get that dot. I just put dots. X equals to 1, and this guy equals to 3, 0. So now the hard part is the explanation. So when I explain geometrically, I need to explain this, and I explained it here. So extracted the parts along the x-axis. So matrix u basically extracted the x component of matrix x. As forming a projection of matrix x along the x-axis. I believe that's what's happening. Now I'd like to be corrected if that's not. Okay, exactly. All three are correct. One terminology correction. U is a vector, not a matrix. A vector, not a matrix. That's different between a vector and a matrix. Yes. You correctly identified the geometric meaning. Okay. Yes, essentially saying keep the component of x that points in the direction of u, and discard the perpendicular component. That's the hand of projection. Let's make it slightly harder. So like this. This time u is aligned with either axis. So you use this as a u or c of x, calculate this. Question 4. Multiply that scalar by u to obtain a projected vector. Okay. Demonstrating what does the resulting vector mean geometrically? Okay. So what are we dealing with here? 3, 4, and then 1, 1. So 3, 4, and 1, 1. Let me see. This one. Yikes. Okay. I'm going to try and calculate this off head. So this will be 3 plus 4, right? Yeah. 3 plus 4 is 7. And then, yeah, 1 plus 1 is 2. Yeah. And then, okay, so in this case, can I copy this? Let me see. Okay, let's put the division sign. Yeah, no, it's not necessary. How did he mix it? This is definitely not what has to be. How did he mix it? Maybe I copied it from the inside. So this is equals to 2.5. That's 2.5. And then projection. Projection will be times u, right? So 3.5 times 3, what's 3.5 times 3? That should be 10.5. Is it 10.5? Yeah, I think it's 10.5, comma 10.5, and 10.5 times 4. That should be 13.5. And then this equation, and then it's 5 geometrically. Okay. What does the resulting vector mean geometrically? Yeah. Oopsie. Vector u stretched vector x from 3, 4 to what about to 10.5, 13.5 brackets basically scaling. Scaling vector xrel and projecting. Yep. Let me see if I'm right. Okay, you got question 1 to 3. Here is 4, and it exposes an important idea about projection. Oh, is my text finished? Okay, but I got these two compatible correct. Wait, what? Oh, it's one. Oh, no, it was silly mistake. That's such a silly mistake. Oh, for real. So here you will get 1 and 1. You times you will get 1 and 1. You thought you will get 1. For this new one. No. Okay, let me see. So we get x that you get you that these 2. Yeah, that's enough. And that's it. Okay, but now you multiply with 1 and 1. So I guess you get 3.5 over 6. So project is 3.5. So it doesn't stretch from 3 to 4. Instead, we're taking x 3, 4 and we're finding the path of either lies along the direction of u. Okay, so 3, 5 it goes 3.5 and it falls back to 3.5. Okay, so the projected vector lies on the line y equals x. Now that's a freezing traps are freezing. So because u is at position 1, 1, and notice something beautiful. Okay, x minus position of x plus this position of x 3 and 4, 3.5. Oh, 30 minutes already, almost up. So 3.5, negative 3.5. Yes, yep. 30 minutes off. Let's see. Not crazy that I can even see it from the Sobel. Now, if you could stop, my screen is fumbling with me. Okay, it's something beautiful. The remaining vector is perpendicular to you. Check this. That's the key geometric property project. of projection. Okay, you don't understand. No, I don't understand projection. Parallel component, perpendicular component. So projection of x is the parallel. Now x is 7 minus square root of the that's true. Okay, that's true. This decomposition is extremely important later for things like PCA. Still one short PCAs. Now, Eugene vectors and Eugene values. Oh, let's use anyway. Projection. I still have projections to work on. This Eugene values. I'll stop at Eugene values. I want to go and learn CNN now. So, I'll end at projection. Boom. Some computer vision stuff. Yeah, let me just share this my daily log again so you can feel what I need you to feel. Oops, that is not what I wanted. So once you feel that, stop the applications. Yeah, although I would like to work more on projections. But I understand the basic idea on it, but still need to work on that. I'd like to increase this. Okay. So then save this here, remove this. Leave this row. 28. D6, okay. I'll take it. If possible, let me just set on this. Whoa, this is not going to do. How am I going to show that? Okay, for now you won't be able to see me for now. What is running? Just yes. Let's sort of fix this. Mesh cell, not mesh cell. What I want to do is swap. Oops, let's swap. Yeah, that's what I want to do. Alright, no, I don't even know. Oh. Expected hours. How many hours has the stream been so far? I wonder. Okay. I'll just copy this to as usual. Copy. Paste here. Oops. Yeah, match these guys. And then match these guys. Remove this column. I did the GitHub, so okay, live. Why are you making this so long? So the 6 mathematics contribution in algebra, yeah. Vectors, the product, matrix multiplication, operation, Linear transformation, yep, projections, you have still have to test this. Build and tested live OpenCV convolution visualizer with Sobel, Prewitt and Laplacian filters. Visualize kernels, take the image, how long has this stream been? I wonder. It's hard to tell. Wait, I think I come from OBS here. Let's check OBS. How long has this stream been? 2 hours 30. Okay. 2 hours 30. So that's like 2.5. It's not bad compared to yesterday. 2.5. Okay, so what was achieved today? What I learned. So I learned strengthening, understanding of vectors, matrix, transformation and projections, connected convolution and classical edge detection. Then why Sobel respond? That was easy. It was easy. But it was kind of easy. Working live convolution, edge detection, and that. I think at this point, GitHub shouldn't even be part of this. Anyways, maybe when I do a project, I'll just set post it on GitHub. Anyway. So, what is this? Notes. Okay. Stop at projections as planned. Aging values, aging vectors will contain extension. Yep. Aging values is interesting. So, only my dashboards. So, I've actually 85. No, I've not. Oh. How long? So, let's go. Oh, what time? Alright. 65%. Oh. Okay. I wish there's a way I could like follow over that course.
Going to copy this code. I'll explain it briefly, but I'm not going to go through this particular code line by line because it's not.
How am I going to do this now? It's okay, I can get this video on YouTube, but I don't have troubles resharing this, from the live. But this is what I'll be looking at. Let me see now. I'm going to be following this one. Just end the stream now. So I might just end the stream now. I might as well just end the stream now because I have to go and continue learning on computer vision. This is what I've been learning though. And feel free to join. You should definitely join. It's really interesting. By Visual. Posted like 1 year ago. His PhD holder. Let's check it out. It's amazing. If you're into computer vision, I really recommend. But guess I'll be ending this stream here. My stomach is bloated. Okay, so if everything goes well by tomorrow, I should be a neural network savvy guy. You know, if everything goes well, that is. Let's see something. Right, time to end the stream and work more on other things. To focus. This lecture. Stream was on for like how long? Stream was on for like so I could say start that. And having this Sobel like filter and stuff. That's a great step. That's a really good step. Look at the notice this. Wow. Can you make sure I think you saw it? I thought you found it. Let me see if I press P. And then the stream, goodbye. Peace.